Hi, ET250. I just wanted to go over this kind of issue with the Lab 10, and hopefully this explanation helps. And so my understanding is that you guys are having a situation where you're looking at the phase of a resistor, a capacitor, an inductor, and then I also believe a resistor and a capacitor or a set of capacitors in parallel, right? So let's just look at what we got going on. So in all cases, we have V and I, is that right? And so just to review our impedance for all these guys, what do we have? R angle 0 degrees. What about for this one? This is 1 over omega L or omega C with an angle of minus 90 degrees, right? Because this is the same as 1 over j omega C. For the inductor, what do we have? We have omega L with an angle of 90 degrees, right? Because this is the same as j omega L. And then what do we have for here? This is a weird one. We'll come back to this one. And I believe what you guys had in your lab is you had a bunch of columns that you had to figure out. You had to know, or you actually computed the VRMS, the IRMS. You had to get the real power. So you got some measurements here. So with these measurements, you could actually find the cosine of theta V minus theta I, which we call the power factor. Is that right? Now, these were measured. And I believe you had to figure out what this theta V minus theta I was from all this data. And if you recall from our lectures before, we have P equals IRMS, VRMS, cosine of theta V minus theta I. And this is the real power, right? And what's the real power? It's the average of the instantaneous power. And this is essentially the apparent power. Okay. And we have this as our power factor. Now, let's say I want to calculate this. So I know this one, I know this one, I know this one. Well, that's not too bad. I can just do an A cosine of what? So power factor equals P over I RMS V RMS, okay? And that equals our cosine of theta V minus theta I, okay, no problem. So theta V minus theta I is equal to the A cosine of P over I RMS V RMS. Yay. So this would be essentially your measured power angle. So we'll call this the power angle. And I believe you guys have the symbol phi or theta or something like this, or capital theta, sorry. Okay. All right. So then I believe there's a column here that goes, well, what is your theta theoretical? Okay. Well, don't forget from your complex Ohm's law that your Z is equal to V over I. Right? This is your complex Ohm's law. So in fact, your phase of Z here, remember Z is actually Z theta Z equals V theta V over I theta I. Your theta Z is actually theta V minus theta I. So if you're looking at an impedance here, and all these are impedances, your theta Z value is equal to phi. Oh, that's nice. So if we were to look at one of your columns where you just had a pure resistor, I believe, your phi for the, how do we say, theoretical is just 0, right? Now you're going to measure probably something here when you do this calculation, your measured theta is probably something close to 0, so approximately 0, but this column here should all be 0, right? Okay, no problem with that. And what's your power factor? Your power factor is 1. So here for your P, it's just going to be VRMS IRMS because this is 1 for your power factor for a pure theoretical resistor. Now, I believe you also have an inductor, right? So what should be your phi theoretical? Well, it should be 90, right? Your theta V minus theta I was this guy. It should be 90. Easy. Now, what about your capacitor? Your capacitor, what is it going to be? It's going to be minus 90. It's going to be this guy here. No problem with that. Okay, so this one will be close to 90. Now here, when you do your A cosine, you will get a positive number, right? But you have to know to put the negative here because remember, cosine is a symmetric function, right? So if you have theta V minus theta I, if you know this value, you know this value, right? You don't know if the sign is positive, negative, but because we know it's a capacitor, we know we're on the negative side. Anyways, okay. So here, your power factor should be 0 for the theoretical, right? And remember, the inductor and the capacitor, they bounce energy back and forth. So they have all Q and no P, no average power, right? But the instantaneous power could definitely be non-zero. Okay, so hopefully that's all well and good. let's go to the last one. So the last one, I believe, is the trickiest one. So you had a bunch of resistors, R1, R2, R3, blah, 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 blah. And then you go C1, C2, C3, blah, 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 blah. Okay, well, at this point, it's easy. You just go at 0, 0, 0, 0, right? And then VRMS, VRMS, IRMS, VRMS, IRMS. Okay, great. That's easy. So when you add all these up, you get something in parallel. I think it's like 80 something, approximately 80 something for all these in parallel. Okay. And then it gets tricky because now you have a situation where you have a resistor and a capacitor in parallel. So you have this resistor here, or the equivalent parallel resistor, R equivalent parallel total, we'll say. And then you're going to add a capacitor. And then you're going to measure the voltage and current, the real power. And then you're going to add another capacitor, and you're going to do the same thing in another one. Okay, so you got C1 and C2 and C3, so on and so forth. Okay, so then you might say, well, how do I get this theoretical phase angle for these guys as I keep adding more capacitors in parallel? Like, don't forget, you still have this approximately 80 ohm resistor. Well, let's break it down. So what do we got? We got R equivalent total. We'll just call it R for now. And we got, let's say, a C. So let's do this. So we got an R and a C. Okay. We got a V going in, or sorry, a V across and an I going in. Okay. So this whole thing can be represented as a total Z equivalent. And remember, for our phasor stuff, we treat both of these as if they're resistors. So this looks like two parallel resistors. So Z equivalent is equal to ZR times ZC over ZR plus ZC, because this is our parallel rule. And now we can plug in our impedance values for these. This is R, 1 over j omega C, R plus 1 over j omega C. Okay. Not too bad. We can multiply top and bottom by j omega C. Great. And what do we get? It's actually squeezes out to something nice. This cancels. So I have R over j omega RC plus 1. This looks actually pretty familiar to our high pass, low pass kind of derivation in the last lecture. All right. So if I have this, what's going on? It's in rectangular form, and I'd like to get it in polar form, and I'd like to find the angle of Z equivalent. That's really my goal here, because the angle of Z equivalent is my theta Z, and my theta Z is theta V minus theta I. Good. So I want to convert this into polar form. So what do I have? R angle 0, and on the bottom, polar form, well, that's easy. That's just the Pythagorean theorem, 1 squared plus omega RC squared. We don't really need this, but I'm just putting there for fun. And then what about this one? Well, don't forget, you have a y component, x component, and it's a right triangle, so we can use our inverse tangent friend, and it's the y component over the x component. Great. So if I want to just look at the phase of this, it looks like this, 0 minus, because when I divide phase, I subtract. So this is actually negative tan inverse of omega RC. And if you go watch that high pass, low pass filter impedance lecture, okay, then what you can do is we actually covered this. This looks like this, omega RC on the x-axis, and it goes at 0 and goes down to minus 90 degrees. That's what this function does. So that's what this guy is going to be in here. This is actually minus tan inverse of omega RC. Okay. Okay. So let's get some intuition behind this. So you're telling me at no capacitance, right? Then this goes to 0 and we're here. Yes, I am. And would that make sense? It sure would, because a resistor, a pure resistor, has 0 degrees phase, right? Theta V minus theta I, okay? And as I keep increasing the capacitance, I keep going this way. And if I have a big enough capacitance, it's like a capacitor, the resistor kind of gets nullified, and I get to minus 90. Does that make sense? Yeah, it sure does, because a pure capacitor has minus 90. Okay, good. So that means the theta V minus theta I for this resistor capacitor combo is going to be somewhere in between 0 and minus 90. So like this. Okay. Did I write that correct? I think it should be this way. Sorry. Less than theta Z, less than 0. Okay. All right. So let's again dive in. So we got theta Z is equal to minus tan inverse of omega RC. Great. Okay, so what is this R? This R is going to be the approximately 80 value, right? Because what you've done is you've now parallel added all those up. Okay, now on the first row here, what are you going to do? Well, you're going to use C1, right? And now on the next row, what do you got to do? Well, the next row, you're going to use the approximately 80, but now you got to cumulative add it because capacitors in parallel add. So you got to do C1 plus C2. So you probably want to keep track of that, right? So you probably want to put somewhere, add another column, and you have C1, C1 plus C2, C1 plus C2 plus C3, if that makes sense, so that you keep compounding, adding these capacitor to this equivalent capacitance, but this resistance stays the same. If that makes sense. Okay. So I think that will help you figure out what the phase angle is. Now, how do I calculate the real power now? Okay. Well, the real theoretical power is going to be still V RMS I RMS power factor, but now you're going to say cosine of this theta z here, because theta z is equal to the phi is equal to theta v minus theta I. Okay, not too bad. Let's go to an Excel shot, a screen where Professor Clyett was actually, he built some data out, and let's see if this makes sense. So I'm going to share screen, and I'm going to go to the spreadsheet. And so let's look at the spreadsheet. So in the spreadsheet, what do we have? We have the phase angle for the resistor is 0, theoretical, right? And the phase angle for the inductor is 90, theoretical, makes sense. Minus 90 here, great. And then look at this. This was the total equivalent impedance. It ended up being, or resistance, it ended up being 83 when you put them all together. And then look at this. Here's the theoretical, and it's the, oops, sorry. It's the, not this one. It is, excuse me, it is this one here. It is a tangent, negative a tangent of omega RC, where this R is the 83 and this C is this column here. And then I have a negative, right? The 377, where's that from? That is from 2 pi times F, which is 60 Hertz. Okay, and now let's be careful here. Notice this is in radians because Excel likes to output radians. And look at the value that it's taking, C34, which is this one, that's fine. But when we go to the next cell, look at the equation C35, it doesn't take the 16, it takes the 0.00032, which is the addition of the 16, right? It keeps on adding the next capacitance here because we're adding the capacitance in parallel, okay? So I hope this this little YouTube video helps you out with your understanding of the Lab 10. And the last thing I want to leave you with, I'm actually going to come back to here. So let's stop share. Let's come back to the doc cam. Is this. So if you have a resistor and a capacitor in parallel, and even though you keep adding capacitances, the real power should stay constant, right? And why is that? Because the real power is only being burned off of this resistor, right? Technically, for a pure capacitor, the real power, even as I add more capacitors, should be 0. Okay, and why is this constant? Because the V never changed, right? Okay, well, what is changing? There's got to be something that changes as I add these capacitors. Sure, more I is being drawn. Is that right? So if more I is being drawn, that means the S is going up. The apparent power is going up, even though the real power is going down. So as I add more capacitance, the power factor is going poorly, even though we've maintained a constant P. So if I were to look at the power triangle, I would see this, P like this, and then maybe here's S. But as I keep adding more capacitors, what's going to happen? I'm going to get something like this, and like this, and like this, and like this. Okay, so I hope that makes sense. All right, well, I'll see you in class. And like I said, I hope this helps.